Okay. So the exponent laws, all these are in the book, and you can look through them, but I want to totally talk about kind of why it's happening, why it's working the way it is. So, x to the third, what does that mean? X times x times x, right? It's repeated multiplication. Just like if I had a 3 times x would be repeated addition, this is repeated multiplication. So it's symbolized with our exponent, which is our way that we symbolize repeated multiplication. All right, this is very similar to what we just did, right? This is x to the third, and then that quantity squared. So, if I was to do my repeated multiplication, it becomes x to the third times x to the third. And if I apply the rule again, I would get how many x's? 6 of them. And so we generalize that, and that's what Jessica was talking about earlier, is if I have a power of a power, I just have to multiply to get the whole thing. All right, but it's always just going back down to the definition of what an exponent is and what it does. All right, if I have the same base and I'm multiplying, I just add the exponents. So if I'm multiplying, I add. If I'm raising to a power, I multiply. So the common mistake that you see is people think if I multiply, then I multiply, and if I take the power, then I take the power. So people will sometimes say this is x to the 9th, and this is x to the 9th as well, which wouldn't make sense. Right? So if you get confused, just write it out. See how many x's there's supposed to be. All right, just repeat the multiplication, see what you got. All right. X to the third over x squared. Well, if I expand the top, it's x times x times x. The bottom is x times x. Well, I can cancel some of these because x divided by x is 1. X divided by x is 1. And how many x's am I left with? 1. All right, 1x. And if I look at my exponents with 3 and 2, how do I get to 1? You subtract them. So if I'm dividing, I subtract my exponents. So multiplying, I add. Dividing, I subtract. Power to a power, I multiply. All right? Good so far? All right. So what about the negatives? Well, let's look at some patterns here. We can do this 2 different ways. One is to look at a pattern, and this is usually the easier way to think about what's going on. So if I start with x to the first, x squared, x to the third, and x to the fourth. So I'm going to expand those in terms of what they are. That's x squared, that's x times x times x, and that's x times x times x times x. So that's the definition of what an exponent does. And now I want to look at how do I get from one step to the next. Well, I multiply by x to go up, right? Well, if I want to go the other way, if I want to go down, instead of multiplying by x, what would I do? Divide by x. So I divide by x to get x to the third. I divide by x to get to x squared. I'm not subtracting an x, right? Because if I take away, this is x to the fourth minus x does not equal to 3x's. If you do it with numbers, it'll work the same. So if I start my pattern and I divide all the way down, what would the next one be? X to the 0, and what would that equal on this side here? 1. X divided by x is 1. All right, and as Josh said, my powers are decreasing by 1. I'm subtracting 1 each time. And so 1 minus 1 gives me 0. So x to the 0 power is 1, always. Unless the base is what? 0. So if I was to take, and this is a really common test or quiz question, x to the third times 4.68 repeating y to the negative 48 all over z plus 2 to the third. For the 0 power, evaluate without a calculator. What do you get? 1. All right? It doesn't matter. Unless this is 0, which in this case it wouldn't be, it's going to equal 1. All right, so anything to the 0 power is 1. All right, well, if we continue this pattern, we're going to start to get negative exponents. So if I go down again, if I divide 1 by x, what's my expression? 1 over x. 0 take away 1 is negative 1. All right, if I keep going, now I get 1 over x squared. So we can see our pattern of what's happening here with our negative exponents. Do it again. X to the third. So x to the negative 3 is 1 over x to the third. So in general, x isn't 0. And why is x not 0? Can you divide by 0? No. So x to the negative power is 1 over x to that positive power. All right. We good with that? Do we understand a little bit more why the negatives are doing what they're doing? All right. So the question is, are these values positive or are they negative? I'm getting closer and closer to 0, right? But I'm not getting negative numbers. So we're going to look at the graph of this down the road. So we're assuming that x is positive here. 1 over something to the positive 3 power is going to be a positive number. So we're not getting to negative values. We're just getting closer and closer to 0. All right. So that's really all there is in section 6.1. It's the exponent laws that you're used to. It's applying them to things that look scary. But it's just applying those rules as we go through. We'll do some examples in a little bit. But let's talk about operations with polynomials. So all we're doing here is adding, subtracting. That's easy, right? Because multiplying, there's 2 ways to do it. Let's just do one. I don't think I even put one in here with adding, subtracting. So if I was to take 2x to the 4th plus 3x squared minus 16 plus another polynomial, 5x to the 5th minus 2x squared plus 4. I need to add those together. What am I looking for? It's 2 words. One begins with an L, the other begins with a T. Like terms. So like terms have 2 things. They have the same base. They have the same exponent. So how many other x to the 4ths are there to combine? None. What's my highest power that I deal with? The 5th. So I'm going to start with that. And then I have 2x to the 4th. How many x to the thirds do I have? 0. So I could put a 0x to the 3rd. I'm not going to do it. And then I have 3x squareds minus 2x squareds plus x squared. These are my constant values. Negative 16 plus 4. So that should be pretty easy. Subtracting is very similar, except you have a subtraction out there and you distribute it through. If you can't do that, you need to talk to me. Multiplying gets a little bit trickier just in terms of keeping track of what we got going on. Stretching or question? Sure. One is algebraic and the other is geometric. This is very similar to how we looked at completing the square. But algebraic, let's say we had something that looked like this. Multiply x minus y times quantity x squared plus 3x minus 4. So what we could do is we could distribute this x plus y through and then distribute it again. So double distribution. But if there were 3 terms here, I'd have to triple distribute. And it's easier to forget what's going on. Or we can do it the way that you learned to multiply way back in 4th grade. All right? So if we set it up, all right? Remember when you multiplied numbers like this? And I'm going to multiply through that negative y times negative 4. It gives me 4y. And then I multiply the y by 3x. And then the negative y times x squared. All right? I add a placeholder, just like we would if you're multiplying numbers. And I multiply through by the x. and I get x to the third plus 3x squared minus 4x. And now I have to add them up. X to the third minus x squared y plus 3x squared minus 3xy minus 4x plus 4y. Are there any like terms that I can combine with that? So I don't have any other x to the thirds, I don't have any other x squareds y, I don't have any other x to the x squared, x y's, x's, or y's. So that's as good as it gets. I don't particularly like that way because it's easy to make mistakes. The way that I like to look at it is geometrically. So I'm going to draw a rectangle. And I'm going to put all my pieces in there and I'm going to see what I got. So x squared, 3x minus 4, x minus 1. So I had 3 terms in this polynomial, so I have 3 columns, and I had 2 terms in this one, so I have 2 rows. And then I just figure out the area of each box. So what's going to go in this upper left box? X to the third. This one's going to be x times 3x, which is 3x squared. I fill it in. All right. And if you notice, I think I color-coded this the right way. All the red terms that we got here are exactly what we got over here geometrically. And all the terms that we got here in blue are the same terms we got there. So if I wanted the whole polynomial, I just add up my pieces. So this for me is much easier to keep track of what we're doing. All right? It's easier to not lose a piece. But if you want to do it the other way, or if you want to distribute through, you're welcome to do that. Okay. So we add them up and combine any like terms. In this case, we don't have any like terms. All right, and if you want to distribute, go ahead, but it's going to get complicated as well. All right, questions on that?